All right, we were looking in the last class at this problem where we wanted to approximate the function cube root of x by a second degree Taylor polynomial. And then we asked how accurate is this approximation when x is between 7 and 9. Okay, and we went through the process. We went through this problem, and here we looked at the solution, and here's what we discovered. So we found out that, man, I'm always having to adjust this font. There's got to be a way around that, but so the cube root of x is approximately equal to the second degree Taylor polynomial of x, which was 2. So this is the results from the example we covered from section 8.8 in our last class. Second degree Taylor polynomial was 2 plus 1/12 times x minus 8 minus 1 over 288 times x minus 8 squared. And we actually plotted in Desmos the cube root of x function and that Taylor polynomial. And the Taylor polynomial did a good job in approximating this cube root function over when x is between 7 and 9. It did a pretty good job. And we learned from Taylor's inequality that the absolute value of this Taylor polynomial approximation to our cube root of x function, which is the absolute value of t of x of t2 minus the cube root of x, we learned that that was less than or equal to we used Taylor's inequality, and that was less than or equal to 0.0035. Okay, so, and this was, again, this is over the interval from 7 to 9. Notice that the Taylor polynomial is expanded about a equals 8. And so the interval over which we're using the Taylor polynomial is 8's like right in the middle. Now, it doesn't always have to be that way, but it is in this case. So, like, for instance, we could try to approximate the cube root, let's say, of 8.24. What's the cube root of 8.24? Well, you put it in your calculator, you get an answer, right? But how did the calculator get an answer? Well, perhaps an algorithm is programmed in the calculator. A Taylor polynomial algorithm is programmed in the calculator, and they use that Taylor polynomial approximation. Well, let's try to use our Taylor polynomial approximation, the one here, to approximate the cube root of 8.24. So let me go to the solution here. I mean, we really did the solution, but let's test out this polynomial. Let's test it out. Okay, so let's try our approximation to estimate the cube root of 8.24. Well, so the cube root of 8.24, is approximately the second degree Taylor polynomial evaluated at 8.24. And so 8.24 is your x value. That's your x value. So you're plugging in x of 8.24 in the Taylor polynomial formula. And we're going to evaluate the polynomial at x equals 8.24. So when we go through the steps, when we go through the evaluation process, all that's involved in computing this value here, 2 plus a 12th times 0.24 minus 1 over 288 times 0.24 squared, what do you have? You have addition, subtraction, multiplication, and division. Those are all mathematical operations that a computer or a calculator can do. Okay, using flops, right? A flop is a mathematical operation. So we end up finding that the cube root of 8.24 is approximately 2.0198. Okay. So this means then, well, we know that the error here, okay, since 8.24 falls in the interval between 7 and 9, the error in approximating the cube root of 8.24 with our second degree Taylor polynomial has to be less than or equal to 0.00035, right? And if we go to the calculator to get the answer, the calculator would have an algorithm that's going to be more exact than a second degree Taylor polynomial. Maybe it'll have a 20th degree Taylor polynomial, for instance, programmed in it. The calculator answers 2.019803268. So that's our answer's pretty good. Our answer's pretty good. We have agreement here. Let me see. We have agreement to the thousandths place. No, to the 10,000ths place. And actually, that's what we would expect based on the error bound. So our approximation's good. And this is an example of how, I'm showing you as a human, how we would use the Taylor polynomial approximation, and a computer can then mimic what we do, right? And what I did, incidentally, the computations involved, so the computations involved in estimating this cube root of x with the Taylor polynomial involves subtraction, division, and multiplication and addition. And what I did on the next page, I'm just showing this real quick. This is just to show you that I did all the math operations involved in getting the Taylor polynomial answer of 2.0198. I did all of those by hand, okay? And everything in here, all the little operations you've learned how to do, probably since middle school or grade school, right? And so you see, this is how we get things done in math. But again, a computer would have an algorithm like this, a Taylor polynomial algorithm programmed in it. That's one way, right, to get the approximation. And so computer science majors need to be aware of this. And that's how many are computer science majors here? How many are computer science majors? Actually, I know we have a few in here. All right, Ange is, and Jan and Taj, and so yeah, you have to know what's going on, right? What you have to understand what's behind an algorithm to approximate a value, and so great. Are there any questions on this? Okay. Well, what I'd like to do is look at another example. Oh, I just, Mario, I just decided, let's try to estimate 8.24. I just chose 8.24. I wanted the cube root of a number that, like there's no way I know the offhand the cube root of 8.24. That's like a quote, a nasty value, right? It's not something, unless you're a mathematical genius or something, it's not something like, Ramajan or something. You wouldn't know to do that. You probably wouldn't be able to do that in your head, but see, you use the polynomial to help you. And okay, very good, very good. So let us continue on here. Let's do another example. Let me give you a moment to copy this example down. Okay, and then we'll discuss the solution. Okay, so let's see what we have here in this problem. So this time we're going to use a fourth degree Taylor polynomial, which we would denote as t sub 4 of x, to estimate the cosine of 69 degrees. Okay, now the Taylor polynomial formula, okay, as a function of x, assumes x is a number, and 69 degrees is, of course, in degree mode. We want 69 degrees to be in radian mode. So do you remember how to convert degrees to radians? How many radians are in 180 degrees? Right, good, Mario. Pi over 180. That's right, Nathaniel. Very good. So you're going to get 69 pi divided by 180. And that's going to be 23 pi over 60. All right, so anytime you're going to use a Taylor polynomial to estimate a sine or a cosine, you have to have your degrees in radians. You have to convert to radians. So, okay, well, let's look at the Taylor polynomial, or the Taylor series, I should say. So here's the next page. Now, okay, this is, of course, my handout that if you go to the Blackboard and look under course content folder, go to chapter 8, click on that chapter 8, the here link, and find section 8.7, and you will see a link to download this formula sheet. Has anybody tried that yet in course content? Has anybody downloaded this formula sheet at all? Okay, Taj has and Jan has. Very good, very good. So of course on the final exam, and Ange has too. Excellent. Of course, on the final exam, you will have access to this formula sheet. Basically, what will happen is when you go into Examity, there will be a supporting document feature that will allow you to download this handout. Okay, so you can access it. And notice that, well, here's the Taylor series formula right here. And so the Taylor polynomial, well, we would be using the first 4 terms of this Taylor series, or the first 5 terms, I should say, because T sub 4 is a 4th degree Taylor polynomial, so that's going to be a polynomial with 5 terms. So, okay, what though, if I'm going to, I mean, you know, every term I have to compute a derivative of my cosine of x function. But what don't I know? What do I mean, I'm looking here at these terms. Blow that up a little bit. You know, here's f of a. Here's f prime of a over 1 factorial. Okay, f double prime of a over 2 factorial. What am I missing in this problem that I don't know if I'm going to construct a 4th degree Taylor polynomial? What value am I missing? Or what value do I need to know? That's right, Nathaniel. Very good. We need to know what A is. So Taylor polynomials are always centered about some value of A, right? Taylor polynomials are always centered about some value of A. Now, if it's a Maclaurin polynomial, A would equal 0. Okay, so all right, we need to go back to our problem here, and let's see here. Let's list some possible A values. Let me blow this up a little bit. Okay, so possible values of A for the Taylor polynomial. Okay, so naturally, when we choose a value of A, we want it to be a nice value so that we can evaluate the cosine and its derivatives at that value. So, you know, we're going to pick nice values. So, okay, here's some values. Here's A equals pi over 6. A equals pi over 4. A equals pi over 3. Now let me just see. Pi over 6 is, of course, 30 degrees. Pi over 4 is 45 degrees. Pi over 3 is 60 degrees, right? I'm just sort of and maybe we'll have one more, maybe pi over 2. Pi over 2 is 90 degrees. So, okay, we have to pick a value of A, and we should center our Taylor polynomial around the best value of A. Now keep in mind, our 69 degrees equals 23 pi over 60. All right, but we're looking at 69 degrees. So what value of A would be the best value of A to choose so we could get the most accurate Taylor polynomial approximation? Good, that's right, Nathaniel. That's right, Taj. 60 degrees. 60 degrees is the one you want, because that is closest to 69 degrees. So even though you can use the others, you're not really gonna use those. And WebAssign their answer would require you to pick the closest, the value of A that's closest to the angle that you're interested in. Okay, so you have to, before you just go and compute your Taylor polynomial, make sure you're choosing the best value of A. 60 degrees is closest to 69 degrees. So A equals pi over 3. Are there any questions before I move forward? Okay, well then let us proceed on. Let us proceed on here. So, okay, well, we know how to construct a Taylor polynomial. We know how to do that. So here we go. It's a 4th degree Taylor polynomial. So naturally, I'm gonna compute, I have my function cosine of x, and then I compute the first 4 derivatives. And then I will compute the function, the cosine of x and its first 4 derivatives at when x is pi over 3. And I have a little right triangle up here at the top just to kind of help me. 30, 60, 90 degree triangle. That'll allow me to easily compute these derivatives. And for the derivatives, you need to have simplified radical form answers. WebAssign is not going to want decimals. So let me give you a moment to copy down to here. Okay, and let me know if you have any questions. Okay, we got a question here. One moment. Ange, it would not be possible to do like a Maclaurin series. The problem is with the Maclaurin series is all the derivatives are evaluated at A equals 0. You have to evaluate. Yeah, that's the problem with the Maclaurin series. Since A equals pi over 3, we have to, I mean, a Maclaurin series or a Maclaurin polynomial is a special case of a Taylor polynomial when a equals 0, but Ra equals pi over 3. So, okay, well, I just follow then the Taylor polynomial formula and construct the polynomial. You're welcome, Ange. Okay, so let me just I'm just sort of adding a little bit of detail here. It's really quite beautiful, this math, and it's so important. I've seen this and can't tell you how many courses I've seen these Taylor polynomials come up, you know. This doesn't look too good. Let me try to make this look a little better. Okay, that's 4th degree there. Are there any questions on the construction of the polynomial? 4th derivative at the end there. Yeah, yeah. So, okay. So naturally, of course, what we want to do is all the coefficients there. We want to simplify the coefficients. Okay. So, all right. Maybe I'll also. So this is in the recording. That's fine. So of course, 1 factorial is 1. 2 factorial is 2. 3 factorial is 6, because it's 3 times 2 times 1. 4 factorial is 24. 4 times 3 times 2 times 1. So the first coefficient is just going to be negative root 3 over 2. Second coefficient, which is negative a half divided by 2, that's going to be negative a fourth. Third coefficient, which is root 3 over 2 divided by 6, that's going to be root 3 over 12. And the last coefficient, which is a half divided by 24th, that's going to be 1 over 48. Okay. So in simplified form, this is your 4th degree Taylor polynomial. There it is. And you could check this in WebAssign, right? You could graph the cosine of x along with the fourth degree Taylor polynomial, and check to see that the polynomial approximates the cosine nicely around pi over 3. And you understand we call it a fourth degree Taylor polynomial because the last term here involves an x minus pi over 3 to the fourth power. And if you expanded that, you would have an x to the fourth power as a term with an x to the fourth power in it. So that means that's going to be, the polynomial will be a fourth degree. Hence, a fourth degree Taylor polynomial centered at pi over 3. But now what we want to do is we want to use that polynomial to estimate the cosine of 69 degrees. We already established that 69 degrees is 23 pi over 60. So if I'm going to then approximate the cosine of 69 degrees, or the cosine of 23 pi over 60, I'll use the Taylor polynomial and evaluate that at 23 pi over 60. So everywhere the x goes, we put in 23 pi over 60. Everywhere the x goes. And I'll note that, so you have for every expression, you have a 23 pi over 60 minus pi over 3. Well, pi over 3 is the same as 20 pi divided by 60. So when you subtract it, you get 3 pi over 60 or pi over 20. Okay. So the polynomial, the number, I should say, because we're computing the polynomial when x is 23 pi over 60, we have to compute this number. And this is kind of work I would want to see on the final exam. Sometimes students see a problem like this and they don't do the work, and and then they miss points. Okay, and I don't want that to happen, right? I know the calculator can get you values. I know the calculator can do the cosine of 69 degrees. You can get that with the calculator, but you are using the Taylor polynomial now to get that, and so that's how you have to do the problem. When you work this all out, you're going to get 0.3583686. So what I'm going to do is I'm going to go to Desmos and I'm going to type in this and evaluate it. And so I'm going to type in this, whole thing here, this whole expression, and see if I get 0.3583686. So let me give you a moment to copy if you need to, and I'll go into Desmos and I'll join you in a minute. And you go into Desmos too, okay? When you're done here. Okay, I'm going to bring up Desmos. I'm working on plugging all of this in. So let me bring up Desmos. Okay, so I have the first three terms put in, and I want to continue. So let me see here. It's really so beautiful, this stuff, this material. And yep, 0.3588356 rounded to the seventh decimal place. It worked out. Okay, so we have that. We have that. Now, if you were to do, well, yeah. So we want to now see this estimate, this fourth degree Taylor polynomial estimate of the cosine of 69 degrees is 0.358356. No, sorry, 0.3583. Hold on. One moment, class. Oh, there's something I don't like here. Nope, nope. I knew something wasn't right. Hold on. Something's not right here. It's at power. I have to probably, there we go. Oh no. All right, hold on. Sometimes it's just better to build the house over again, right? All right, 0.3583686. But I don't like that there. Yeah, 0.3583686. There we go. Who did get that? Maybe tried it in Desmos themselves and got that? Okay, worked out for you, Ange. Good, good. So the question is now, how accurate is that estimate to the? So the cosine of 69 degrees is there is a value for that, and how accurate is our answer to the true value of the cosine of 69 degrees? How accurate is this approximation, 0.3583686, to the true value of the cosine of 69 degrees? Well, for that, we're going to have to use Taylor's inequality. We're going to have to use Taylor's inequality. Now, I want to just go back to the before I get to Taylor's inequality. I want to go back to this. Let me clear this. Okay, so let's remind ourselves, this is RT sub 4. This is what? T sub 4 at 23 pi divided by 60. And could we use, I mean, again, we're trying to see how accurate, hold on here, let me just look at the phrasing. How accurate is the estimate? Could we use the alternating series estimation theorem to help us here? Do we have an alternating? Well, I want to be a little careful here. Is our polynomial estimate alternating? It's not. That's right, Taj. It's not an alternating polynomial. So we're really going to have to use Taylor's inequality to get to answer the question in regards to how accurate is our approximation. And Taylor's inequality is in the bottom of the handout. Oddly enough, it comes up in section, it's introduced in section 8.7 in the textbook, although we use it really in section 8.8. And we examined this inequality before with the previous example. Now what we want to do is use the inequality again to for this example. So this is the error bound here on the right-hand side, and m is greater than or equal to the absolute value of the n plus first derivative. Well, since we are looking at a fourth degree Taylor polynomial approximation, this means that we're looking then at the error bound of r sub n of x. No, well, I want to be careful. No, we're well, let me just go to the solution here. I don't need to redo this whole thing here, but you've seen Taylor's inequality before. It's going to be on that handout that you'll have access to on the final exam. Let's answer the question here that we need to answer. How accurate is our estimate of the cosine of 69 degrees? Well, to find out how accurate the estimate is, what we need to do, and again, here is the estimate here, 0.3583686. That's our estimate of the cosine of 69 degrees. How accurate is it? Well, we have to use the Taylor's inequality. So the difference between the fourth degree Taylor polynomial and the cosine of x is r sub 4 of x. By Taylor's inequality, the absolute value of the error, r sub 4 of x, is less than or equal to m divided by 5 factorial over the absolute value of x minus pi over 3 to the 5th power. So you established before, when you did the derivatives, you learned that the fourth derivative of x was just the cosine of x. So that means the fifth derivative of x would be negative sine of x. So we look at the absolute value of negative sine of x, and we want to know where's that largest. You know, where's that greatest? Well, where would that be greatest? And we're not really given a range of x values, so we just got to ask ourselves, you know, the absolute value of negative sine of x would be largest. How large can it get? Well, sine and cosine functions oscillate between 1 and -1, right? So the absolute value of the negative sine of x would never get larger than 1, and so you take m to be equal to 1. So this works differently than the problem when we used the Taylor's inequality for the previous example. We looked at the absolute value of the third derivative and saw that it was a decreasing function. And so that told us then how to pick our m value. But in this case, whenever you have a derivative that's a sine or a cosine or a negative sine or a negative cosine, whatever it is, you just let m equals 1. You just take m to be equal to 1, because the idea is we want the m value to be easy, just easy to get, and so we just pick 1. And if you recall back in section 5.9, when you did approximate integration and you had to find the big K values for the error bounds, whenever you had a sine or a cosine involved, you would just replace that with a 1, right? So n equals 1. 5 factorial is 120. And you're putting in 23 pi over 6 for x, right? Because that's the value you care about. And you just figure out what the error bound is. And it turns out the error bound well, let me give you a chance to copy up to here. Please let me know if you have any questions. I'm sorry, I might have had myself off. I don't know if you were hearing me or not. Let me go back to where I was. So I computed the bound on the air as 0.000000797, and that's less than 5 over 10 to the 6th power. Okay, and so that means our estimate is correct to 5 decimal places. Correct to 5 decimal places. And if you go to your calculator and type in the cosine of 69 degrees, you're going to get 0.3583679,495. But the first 5 decimals are in agreement with what the calculator gives you. I mean, let's just assume the calculator is giving you a more accurate answer. Yeah, we have agreement to the first 5 decimal places. So, these are some very nice little problems that we've gone over here for section 8.8. Are there any questions on this? Who thinks this is pretty cool offhand? Who thinks this is, hey, pretty cool stuff here? This material. All right, Todd's just liking it, Ann's just liking it. All right, that's good. I'd sure like more people to give a thumbs up, but maybe you will next week, right? All right, Javier's liking it. Good. I mean, this class, you'll probably make $50,000 more a year, maybe knowing this material, right? Because technical jobs, you tend to get more pay, right? Than other jobs like computer science, engineering, math. I mean, it's just kind of, I think it's, how many have heard that? How many have heard that maybe just from people saying that engineers make a decent salary, computer science people make a decent salary. Yeah, and and that's right. And we love math anyway, but hey, if we can make a little extra money, it's nice, right? Um, okay, great. We love all subjects, uh, you know, um, and we especially love math, right? Okay, I'm going to stop the recording here. We're done with section 8.8. Excellent.